Let me see. Yes. So what we've stopped at was that yes. So the last claim on the lecture, if you see here, was that x of p1, this one, which is the generating function for simple Horus numbers where you put u to 0, right? The simplest part of the generating function for Horus numbers, this guy. Does everyone see where I'm? Let me maybe highlight it somehow. So we're here. U was responsible for the number of transpositions. So the power of u was to the power m, where m is the number of transpositions. Okay? We can see it somewhere, I think. It should be, no, maybe not. Anyway, I guess we'll write it down in a moment. So yeah, and the claim was that x of p1 is a tau function of kp. That was the claim, and we basically proved it on the seminar. Do you remember our definition of what was the tau function of kp? Was that that it's a sum function of p1, p2, and so on, such that under the boson-fermion correspondence, it becomes decomposable in the fermionic space. Okay? Decomposable in the fermionic space, meaning that there exists some beta 1, beta 2, beta 3 elements of V, of our space, infinite-dimensional space V, such that the following semi-infinite wedge product is maps to our function P under the boson-fermion correspondence. So do you remember what was the boson-fermion correspondence? In this space, semi-infinite wedge space, there was a basis, V mu. The basis elements are V mu. Do you remember for what they are listed somewhere here? V mu are like that. The definition is that is z to the power mu1 minus 1, wedge z to the power mu2 minus 2, and so on. So these are basis elements in this space, and there is an isomorphism of this space and the space of our series in p variables, such that we map v mu to the Schur function, to the Schur polynomial S mu. This gives you an isomorphism. So the claim was that if you take x of p1 and then apply this inverse isomorphism, go to the fermionic space, then there exists some vectors that beta I, such that it decomposes in the wedge product of those vectors. And we gave an explicit description of those vectors here. So explicitly, we said that beta I are this, you can actually write it in a more compact form as z to the power minus I times x plus z.
Your yellow is not visible almost.
Okay.
Almost at all.
So this can be more compactly written as z to the power minus I times x plus z. Beta I take like this. This is a series in in Z. You can take the wedge product, this infinite wedge product. You remember that the definition of this infinite wedge product was that, like written here, that we take, once we expand the brackets, we take only a finite number of terms in this product who are not equal to Z to the power minus I. So starting from, once we expand the brackets, we from some point only take the first term there, which is Z to the power minus I, from each beta. We take only a finite number of terms not equal to Z minus to the power minus I. Do you remember this subtlety? So this was our definition of this infinite wedge product. Then it makes sense. And on the seminar, we actually proved this. That indeed, you can see here, on the seminar, we've shown, using the formula for the determinant, and then the determinantal formula for the Schur polynomials, which unfortunately we haven't proved, but there is a claim that it works. Using this formula, the determinantal formula for Schur polynomials, we managed to actually prove that this in fact works. Okay? Any questions so far? Is it completely clear at this point that x of P1 is a tau function of Kp? Is it completely clear what is the statement and how to prove it? Any questions? If someone is unsure that they remember all the steps, please let me know. Okay.
Also, on today on the seminar, we are going to repeat the. So we have a small generalization of this statement to the double Hurwitz numbers. So maybe we repeat at least we repeat the proof of this statement, which Piotr Igorevich mentioned now about that it's a solution of Kp.
Yeah, we are going to actually see that this holds in a more general statement holds. Namely, you have here in x of P1, it was written as, where was it? Like this, yes, where it's a product actually of two Schurs. It's a Schur of P1, P2, and this one is of 1, 0, 0, 0, 0. But one might ask, what happens if you replace 1, 0, 0, 0, 0 with arbitrary numbers, say Q1, Q2, and so on? Can you prove a similar statement? Does it still? So do you remember what was it? It's it's x of sum pi qi over I, and in fact it's also a tau function for arbitrary fixed q, and you can, with very similar reasoning, prove it, and that's what we'll do on the seminar today.
So in other words, if we take a function that is linear in piece and take exponential of that, it's a tau function.
Yeah, indeed. We will see it on the seminar. Yes. Okay, but so far let's complete. We wanted to prove that the generating function for Hurwitz numbers was the tau function, right? X of P1 is, I mean, it's great that we proved this, but it's a little bit simpler function. Not exactly what we wanted, but actually only one small step remains. So let's proceed to that.
Means the coefficients in beta are function depending on Q. Yes.
Yes, but you can actually do this for every. I think this you can do it in several ways. Either saying that they will depend on you, or you can just look at the coefficient in front of u to the power n, so part with and independently prove for each will work. So the claim is that you remember that our generative function. Oops, I'll change to black back. So we said that the disconnected generating function for Hurwitz numbers of u p1, p2, and so on. What was it? It was sum over m from 0 to infinity, sum over m from 0 to infinity, sum over size of mu, sum over mu, size of mu equals m, right? Like that. Then what do we write? We write h disconnected m mu over automorphisms of mu factorial. What else? 1 over, let me write it as u to the power m over f factorial, and then p mu.
Is there a
Is it
factorial
correct?
when we divide by?
Sorry?
Is there a factorial when we divide by automorphism?
No. Thank you. Is it correct?
Can you remind me, please, what p mu is?
P mu means
Product of.
yes, precisely. So if if mu is mu1 and so on mu n, no mu k, then p mu is the product p mu1 times and so on times p mu k. Okay. So that was our definition of p mu, and then we have shown this on the seminars, and you did a similar thing for monotone Hurwitz numbers in your homework, right? So we have shown what? We have shown that this is equal to sum over mu of what? X of sum over box in mu u times c of box. Does this make sense? C of box is the content. Do you remember what was the content of some box in the Young diagram? Let me complete the. We said that this was S mu of P1 and so on times S mu of 1, 0, and so on. So here, if we have some box ij with the coordinates ij, then C of this box is j minus I. Does everyone remember this? So, is it clear the terminology here? Sum over boxes in our Young diagram. We have coordinates on the boxes. It's ith column and jth row. And we say that C of this box is j minus I. And this is called the content. Okay? And we have this formula. We have proved it. All right? Questions? Yeah. Now, what we have proved? We have proved that if you do not have this factor, then we have a k theta function, right? So we have proved that sum over mu as mu p1 and so on as mu 1 0 0. This is a kt tau function, right? So we want to see what happens with this statement once you plug this factor, right? And the claim is that it's somewhat simple. What happens? Let's. Well, we actually want to introduce some new betas. So we said that this guy, upon boson-Fermat correspondence, so we call this. So this guy is kappa. Remember, we denoted by kappa this boson-Fermat isomorphism, right? So we said that this guy is kappa of beta 1, wedge beta 2, wedge, and so on. Where our beta I was equal to some z to the power k minus I over k factorial, sum over 0 from 0 to infinity, okay, right? This was beta I. And now we want to see that our this guy, our Fourier numbers generating function can also be represented as kappa of some beta tilde 1 wedge, beta tilde 2 wedge, and so on. And we want to produce such beta tilde that this works. So let me first give you the answer, basically, and then we will see that it indeed works. So what will be the answer? Let's yeah, so we have this factor x of sum over boxes in mu u of uc of box, right? uc of box. So we have this guy. Let's denote this. Let's represent it as a product of over boxes mu y of, I don't think we have y, so I can use it here, y of c of box. I can do this, so I can say that y of some c of box is an integer, so y of k is defined as x of u k, right? Is it correct? If I define y of k as x of uk, then this holds, right? So y is some function defined on integers in this precise way. Okay. Then we can say that our factor is this product over all boxes of y of c of box. Then let me introduce furthermore. I want to say that I need some other letter. Let me use upper row lambda. Everything is used. I need some.
Just use A and B, just Latin letters.
A.
A, B, C.
Let me introduce A of k, defined over integers again. So this will be product of from 1 to k y of I if k is greater than 0. So k is integer. And 1 over product from I equals to k plus 1 to 0 y of I if k is less or equal than 0. Can I do this? So a of k is another function defined on integers. It's defined as products of y in such a way. Okay? And now the claim is that our beta I tilde, which we want for our KP purposes, is that it should be equal to 1 over A of minus I sum from 0 to infinity A of from over k. A of k minus I z to the power k minus I over k factorial. So the claim is that I want to recall that we had this guy in original beta, and the claim is that if I define A like that, and then I plug it here as a coefficient A of k minus I, and then divide by A of minus I, then this will be exactly what I need. How to see this? How to see this? So we want to take.
Is it true for every function y or
This actually, yeah, this will work for any. Yeah, we will need this later, but in fact, this reasoning works for any function y. Yes. Specifically for simple Hurst numbers, y of k is equal to this, but later on, yeah, y is not. At this point, I'm starting to think that maybe let's rename y to 5. This will be better, right? In order to what you are going to talk about later, right?
Yes, yes.
Y will be better. Yeah, maybe. Sorry, I will.
It doesn't matter, but yeah.
It doesn't matter. But let me just rename, I guess. Ну, это либо у нас обычно либо фи, либо е в степени пси.
Ну, сейчас не важно. Сейчас, мне кажется, можно понять это, а дальше.
Ладно, давайте пока оставим этот y. Можно немножко с ним будет запутаться дальше, когда мы к следующей части перейдем. Ладно, важно. Значит, yeah, it doesn't matter what this y of k is. The reasoning holds. Namely, let's see. So we want to write beta 1 tilde, wedge beta 2 tilde wedge, and so on. And we want to express it as some, with some coefficients, C mu, V mu, right? So we want to represent it in terms of this basis V mu. And then we know how our boson-fermi correspondence works, right? So kappa of this guy will be equal to, so we want, in fact, to show that, you can see here, if we want to show that this is equal to H tilde, then we want to show that this is, this will be equal to this guy, right? This factor times S mu of 1, 0, 0, 0. So we want to show that C mu, once we represent it in terms of this basis V mu, we want to show that C mu is equal to, in my notation, this will be product over boxes in mu of what? Of y of C of box times S mu of 1, 0, right? This is what we want to show, and then everything is proved. Do you agree? Is it clear that what remains to be seen is that once we take this product, wedge product of beta tilde, and then find the coefficients when we express it as a combination of basis vectors, V mu, then we want to show that C mu is equal to this this thing. This is just a factor, and then everything is proved. Do you agree? Any questions? Artyom, do you agree?
Yes.
But all right, we know so far that this works if we didn't have any coefficients A, right? So now we want to see what happens once we introduce these coefficients, this coefficient A. Once we introduce this coefficient A, what happens? You can note that this z to the power k minus I, it comes with what? With the coefficient A of k minus I divided by A over, so we need to take z to the power k minus I. No, wait. So in some sense, what we're doing, we're getting, first of all, an infinite product of all those coefficients. So you get this, actually, it's not, this product might be a little bit problematic once you take the infinite product, but
why is it problematic?
Maybe not. So infinite. That depends on what is your function like.
1 over A is the normalization condition, so that
Yes.
I starts with Z times to power minus I. So this, just beta I is Z minus I.
Yes, precisely. But I want to take out this coefficient from all the terms, and this becomes problematic. But let's just do some formal manipulations at this point, and then we will see that everything works. So formal manipulations, they say that we get a product of
In order to compute C mu, we just multiplicate on the finite numbers.
Yes, yes, we take one. In the end, yes, only finite. Now we know that everything works because we see that they all start with, like you said, z to the power minus I, and we take only a finite number of of all the other terms, then everything works in that sense. But formally, you can say that you have this product from 1 to infinity, 1 over a to the power minus I. This is what this part comes into play where, and then you have all the z. You see that in V mu, how does V mu look like? What is V mu? V mu, if you remember, it's z to the power what? Mu1 minus 1, wage z to the power mu2 minus 2, wage and so on, right? And we see that where do those z to some powers come from? They always come from our beta i's in this wage product, right? But every z to the power to some power m, it comes with the coefficient a of m. No other way, right? Do you agree? So what happens with this guy? Once you plug this coefficient, it transforms into what? Into a of mu1 minus 1 times a of mu2 minus 2 times and so on.
Times V.
That's what?
Times V. Initially.
Yeah, times v mu. Yes, you're right. Times v mu. So this will be a prefactor, right? But we had also this prefactor, and this comes from every z. Every z comes with this a of minus I, so we can actually say that from this product, what we get is that they all come with a of mu1 minus 1 over a of minus 1. So from this prefactor, you have that this comes with a of minus 1, a of minus 2, and so on. Right? So in fact, what's more correct is to write it like that. Do you agree? Is it clear where those denominators came from? But now let's compute what happens with what is this guy? What is this guy?
Could you remind me where the... okay.
What is this guy? What was our...
I have no questions.
Okay, so claim that a of k over a of l is actually easily represented as product from over I from k plus 1 to l y over I. Do you agree? This is directly coming from the definition of A.
Носка обычно больше, чем L. Не должно быть.
Что-то поменять может.
Нет, L просто наоборот.
Yes.
Определение.
Мы в данном случае считаем, что KL не отрицательный, правильно?
Но нет.
Yes.
У нас все определено.
Как раз они могут быть отрицательными, но k больше L.
Yes. So, они могут быть отрицательными, но k больше L, да. Yes, thank you. Is it correct? Now let's go back to our definition of A and see this. So our definition of A is this. I mean, it's clear. Even if some of them are negative, then this still works due to this definition, right? So what does this mean? This means that we have that this guy, the orange guy, is equal to what? Can someone tell me? Using this fact, how can I rewrite this?
It's a product of y over components of the row.
Well, yes, but how to? It's a product. The first guy, who will be? What will it be?
Well, we take all the contents of boxes in the first row.
Yes, we take the first row, and this means that. Well, I mean, let's at this point let's write it explicitly. So it's a product of what? From
It is a product of products.
It's a product of products, but what was the first product?
From 0 to.
Let's take the product over J1 from 0 to what?
To
mu1 minus 1.
Mu1 minus 1, y of J1, yes, times what? Product from J over J2 from what? Minus 1 to mu2 minus 2 y of J2, and so on. But what is this? What will these J's, what values will they take? Let's look at our Young diagram, right? What does this correspond to?
Как он нас не написано?
Let's see how to put them so that this is correct. What is the contents? The content of the lower left is 0, right? It's 1 minus 1, right? Here the content is it's 2 minus 1, right? So oh sorry, it's 1. 1, 2, 3. Here it's minus 1, minus 2, minus 3. Here it's again 0, right? Here is 1. Here I have written contents inside. And you can see that if our mui's are the heights of the columns, right? So if here so I have mu1 equals 4 here, mu2 equals 3, mu3 equals 1, mu4 equals 1, okay, in this picture. Then this product is just the product of all the contents in the first column, right? It's y of not of all the contents, but of y applied to all the contents in the first column. Y of 0, y of 1, y of 2, y of 3. It's mu1 minus 1, 3. Then I get this second one. It starts from minus 1, exactly. Then of 0 and 1 and so on. And this is correct. So I'm saying that this is indeed what I wanted. It's product over box in mu, y of C of box. That's it. So we just used the reasoning from the previous problem where we proved for x of p1 and then looked at what changes. And we said that every z to the power mi minus I comes with this factor if we change the betas like that. Does everyone agree with that? Any questions? So we have proved that the generating function of first numbers is a top function of KP.
А я же правильно понимаю, что CMU это мы вот сейчас ввели какую-то переменную, ну то есть раньше она не встречалась.
Да, это мы просто сейчас обозначили коэффициент предложений по базису вот этого вот вектора в пространстве полубесконечного внешнего произведения. Мы, еще раз, как работает бозон фермионного соответствия? Мы говорим, что берем произвольный элемент, например, вот этот, из нашего полубесконечного пространства полубесконечного внешнего произведения, раскладываем по базису v-μ, и дальше каждый v-μ заменяем на s-μ в длинном шуре. Коэффициенты остаются те же. Это получается то, что в бозонном пространстве. Нам надо таким образом, мы знаем, что у нашей производящей функции чисел вырваться, коэффициенты были вот такие. Это мы выше. Если мы проверим, что у b, когда вы их разложите по базе, коэффициенты совпадают с этими, то все победа.
Ну, точнее, можно даже логику наоборот понимать, да, что нам достаточно предъявить такие бета, которые при бозон-фермионном соответствии в обратную сторону дадут те коэффициенты, которые были в условии утверждения изначально.
Ну, это не в обратную сторону, а так мы и говорим, что...
Ну, да, да.
Увидеть, что оно разложимо, мы хотим предъявить явно
Да.
вот таких бет, которые...
И вот просто они явно предъявлены, да.
Окей?
Мы вроде как изначально хотели, это мы доказали при любой функции y.
Да, на самом деле мы действительно здесь никак не использовали, что наша y, вот такая. Видите, в нашем рассуждении. In our reasoning, we haven't used anywhere that y of k is x of uk. It works for any function y of k over integers.
We use that it is non-zero.
We use the distance zero, yes.
But, so my question is about another thing. Here we proved for coefficient s mu of 1, 0, 0, 0.
Yes, yes. What happens if you replace 1, 0, 0, 0 with something?
Yes, with some parameter.
We'll do this on the same precisely. I will state this. So what I was going to do right now is to state the claim of what happens for S mu of any parameters, and then on the seminar we will prove that it works.
Можно еще вопрос? Можно вверх?
Yes.
Вот. То есть, если мы убираем экспоненты, то он не зависит от P2, P3 и так далее. Если добавили, то зависит, а в экспоненте нет ничего от зависимости P2, P3.
Ну,
просто оно так хитро сокращалось.
Так хитро сокращалось, да. Просто так устроены функции пыльного шура, что они между собой как сокращают все эти, ну, что все вот эти остальные переменные p сокращаются. Ну, просто в базисе p-μ это довольно удачно получается представление, но это такой выделенный базис. Но здесь все нормально, потому что когда вы в базисе S-μ, то там все базисные элементы представлены в этом предложении. И вот это наше рассуждение, что мы смотрим, как меняется коэффициент, оно работает, потому что они все это видят. Ну, совершенно справедливый вопрос, но да. Просто оказывается, что если это рассмотреть в базисе по нему, то он оказывается очень специальным, там почти все сокращается в исходной штуке, но не в базисе. Еще вопросы? All right, so now I will formulate the general claim. From which we'll start the next part, the second part of the lecture. already regarding. Okay, so the claim is that oops, let me use black. Let z be equal to sum over mu x of sum of boxes in mu psi of h bar times c of box. I'll introduce some new functions. I'll explain what this means. Times s mu of p1, p2, and so on, times s mu of q1 over h bar, q2 over h bar, and so on. So for any, and the claim is that, let me see if there's some condition on psi which I want to say. So for any formal series psi of theta equals to sum from k equals to from 1 to infinity ck theta to the power k, and any q1, q2, and so on. Z is a KP tau function. Zero. What is the difference with what happened above? The difference is that I do not have U, but I have H bar. This basically means that if we take simple Fourier numbers, if I instead of putting U to the power m, if instead I will put H bar to the power to G minus 2 plus m, do you remember what was this? We had the Riemann-Hurwitz formula. We have this side note, so that Riemann-Hurwitz formula says that m is equal to G minus 2 plus psi of mu plus L of mu. This was for simple Fourier numbers. For simple Fourier numbers.
And maybe write down for double Fourier numbers also.
Yes, for double Fourier numbers, it's m is equal to G minus 2 plus L of mu plus L of mu.
Там род просто для связанных и не связанных одинаковым образом.
Род полный, ну, хороший смысл имеет, на самом деле, чтобы как следует говорить о роде, надо говорить про связанные. Про несвязанные, с несвязанными есть некоторые тонкости, поэтому на самом деле, вот, когда появляется G, это нужно, ну, если мы хотим раскладывать по G, лучше перейти к связанным. Утверждение на уровне связанных лучше делать, но на самом деле это не очень принципиально.
Ну, та функция, которая сейчас написана z, это не связанная.
Нет, можно дать алгоритм и работать с алгоритмом, который будет отвечать связанным.
What is double Hurwitz number?
What is double Hurwitz numbers? It's when you have 0, infinity. Here I have mu1, mu2, mu3, and so on. So over infinity, my ramification looks like mu1, mu2, and so on. Okay. And over 0, my ramification looks like nu1, nu2, and so on. And then I might have some number of simple ramification points. M simple ramification points. So the usual double Hurwitz numbers are they differ from the simple Hurwitz numbers by that you fix another point and fix the profile there as well. In terms of permutations, is that you wanted to say that m positions times permutation of cyclic type mu should be equal to identity, and you count all combinations, all collections like that. And here you say that m transpositions times a permutation of cyclic type mu times permutation of cyclic type mu is equal to identity. So you add a permutation of cyclic type mu for fixed mu into the mix. Okay?
It seems that here should be plus minus 1.
Where?
Because if we take mu equals to 2, 1, 1, 1, 1, oh, no keys.
It's correct, because if you take mu equal to 1, 1, 1, 1, 1, then they agree, because size of mu will be equal to L of mu. If mu is trivial, if over 0 you have no ramification, it's 1, 1, 1, 1. It corresponds to mu equal to 1, 1, 1, 1. Then these formulas agree, as you can see, because size of mu should be equal to size of mu. It's just the number of sheaves over a regular point, right? And then if mu is 1, 1, 1, 1, then its length is equal to its size. And then these two formulas, they are precisely equal. Okay? So it's correct. But anyway, so the point is that if you let's at the moment look at simple Hurwitz case, then M and G are related like that. And the claim is that if you replace our U with H bar such that you plug it over here, in particular for simple Hurwitz numbers, you write 1 over H 0, 0, 0, 0 here. Then this will agree with the formula above. And you can check this.
So
because what happens? We have u to the power n. This will agree with the formula above.
what do you mean agree with the formula above? I mean, we don't have h bar in the formula above.
I mean that sum over m from 0 to infinity u to the power m over n factorial. Sum over n from I wanted, let's call it L. No, okay. And from 0 to infinity
So now the idea is following. Petr Grigorovich is writing that let's take our usual generating series. So we want to take for disconnected numbers.
Yes. So the claim is that this is equal to sum from g to the power from 0 to infinity to the power to g minus 2 plus. Sorry, it doesn't work.
Without plus.
Yes, sum
Okay, let's
over.
wait because I don't understand. I don't understand in the moment.
Хотим понять, как новую, как доказать старую формулу, поставить новую в один равно чего, когда мы остановим.
One moment. Over. I think it's something like that.
I'm not sure that it's correct.
How to interact with it, because we have variables u on the left hand side and variables h bar on the right hand side.
Yes, yes, a moment.
It's couldn't be correct.
Yeah, maybe.
So what do you want to say at the moment?
I want to say no. Yeah, it's probably not exactly like this.
Yeah, so maybe let's just erase this. So I mean, we do not need any. It's correct.
Just a moment. Yeah, it's a different. Yeah, you're right. It's a different generating function. The claim is that this is in fact. The claim is that this is equal to sum over mu x both sum over box h bar times c of box as mu of p as mu of 1, 0, 0. This is the claim. So remember that you can define, we have this, we have h and mu, but we also have h g mu. Do you remember this? We have h and mu, but we also can write h g mu. It's a different.
It's not correct. I'm not sure that it's correct. So if you put logarithm in the left hand side and then connected Gouritz's numbers in the right hand side, it will be correct. And maybe erase something from the denominator.
То есть вот если в верхней форме определения рода мы разрешаем быть не связанными, то род бывает отрицательным.
Да. Тут что-то не то.
Хорошо, надо для связанных.
Ну да. Надо написать логарифм, да.
А здесь...
Стереть.
Реал, что ли, стереть?
Ну, стереть точку, во-первых.
Точку стереть, да. И, наверное, реал стереть.
Ну, да.
Вот как-то так, да. Yeah, so the claim is that for connected numbers, the number of transpositions and the genus, they are interchangeable. They are uniquely obtained from one another using the Riemann-Kurz formula, right? So you have this this factor, they're equal, yes? But you can write different, for the same numbers, you can write different generating functions. You can write a generating function with u to the power mu, where the coefficient in front of u mu will take care of all the numbers with a fixed number of transpositions, with all the cases with fixed number of transpositions. Or you can fix the genus, and then the coefficient in front of h bar to the power to some power, right? To g minus 2 plus L of mu, that it will fix instead it will take into account the genus of the covariance, right? So these are not equal; they are different generating functions. But one and the same numbers can be arranged into different generating functions. And the claim is that if you look at the generating function which we dealt with u and replace like I wrote here. Sorry, here I want to write 1 over h bar.
Yes, here you should write 1 over h bar.
And replace and put 1 over h bar here in SMU of 1, 0, 0, and replace u with h bar. Then what I'm getting is precisely this other generated function. The one on the right.
No. So if you divide over h bar, you should erase this L of mu on the right-hand side.
No. If I want to erase it, I want to p divide.
Okay. Yeah.
Okay? Is it clear what I'm saying is that, in fact, I can, if I want to not count the number of transpositions, but instead count 2g minus 2 plus L of mu as powers of my additional variables. Then, if I replace it like that, that's what I'm getting. Due to the Riemann-Kurz formula, you can see this actually. You can see this because, where was our Riemann-Kurz formula? It's like that. You can see this because what happens once you plug 1 over h bar here? What does 1 over h bar produce plugged into S mu of 1, 0, 0, 0? Let's see what happened. We had u to the power m. Now we replace u with h bar. Now we have h bar to the power this whole guy, right? This whole guy to g minus 2 plus size of mu plus L of mu. Do you agree? Do you agree? So if we replace u with h bar over here, we have u to the power m, where m is the number of transpositions. Then we get this guy. But then we also put 1 over h bar here. And what does this produce? No.
So we don't see where do you point in.
Yeah, sorry. We put it then over here. And what does this give us? It gives us h bar to the power minus size of mu. Because what is S mu of 1, 0, 0, 0? What happens once you plug 1 over h bar over there in place of q1? The point is that if the dimension is the coefficient, right? But how does q1 enter? It's, you know that S mu is the quasi-homogeneous polynomial of degree size of mu, right? and it's quasi-homogeneous in its variables, Q1, Q2, and so on. But if it's quasi-homogeneous of degree size of mu, then Q1 should enter as a Q1 to the power size of mu. And with all the other guys are equal to 0. Which means that once you plug 1 over h bar here, you still get the same coefficient, the dimension over the factorial, but multiplied with h bar to the power minus size of mu. Is it clear?
We can do the same to consider P1 over h bar, P2 over h bar square,
and get rid of this guy. Yes. But at this point, I want to do it here. So if I put it here, then I get precisely h bar to the power minus size of mu, and this cancels.
So you discussed what now?
In general case, if I have not zeros, but Q1, Q2, and so on, and I divide all the Q's by h bar, I get rid of this L of mu from here. And if I also divide P by h bar, then I can get rid of L of mu.
So maybe let's see. So yeah, if we have Q1, Q2, etc. here, then maybe let's see that if we divide. So maybe let's see in this example, if we divide each P1, P2, P3, etc., then we get rid of this L of mu. Yes.
Maybe let's discuss it on the seminar, I think.
Yeah. Okay.
Anyway, so you see that if we're looking now at this guy, then for when all the CKs are 0 except of C1, which is equal to 1, if psi is just equal to theta. Then we get the generated function for, and all the Q's are equal to 0 except the first one, we get the generated function for simple Hurst numbers. And if, for instance, psi is equal to what? To logarithm of 1 plus theta, something like that, you will get the monotone Hurst numbers. And if you allow Q's, arbitrary Q's, you will get double Hurst numbers.
So if we have, in fact, if we have a finite number of non-zero Q's, or for example, Q1, Q2, etc., QL, and psi of theta also is equal to just theta, then we obtain double Hurwitz numbers, which we discussed below.
No, in fact, you need to take a coefficient in front of. If you want to fix nu, then you want to take the coefficient in front of q nu of this generated function. But anyway, we'll discuss this a little bit later. But this will be our main object with which we work. So the thing is that we want to take this guy, and then it turns out that first of all, it includes all known cases of Hurwitz numbers and generalized Hurwitz numbers. You need a little bit, so for some more advanced cases like what's called the R-spin Hurwitz numbers, or the Ruribaffa generated function for whole polynomials, you need a little bit more complications, namely that you need this psi to also depend on h bar. This might happen. This psi might also depend on h bar.
Piotr Igorevich means that this definition of psi, so here psi of theta is equal to just some formal power series in theta, and here it might depend on h bar itself, not in the formula, but here in the definition.
H bar only enters as written here, this expression. But you can also say that your CK also depends on h bar, and this is needed sometimes for some more advanced Hurwitz numbers, but we will skip it for now. So, but this is still very general. It includes the simple Hurwitz numbers, the double Hurwitz numbers, the Buscema-Schiffer numbers, the monotone, the strictly monotone. Many cases known from the literature of Hurwitz numbers are included here. And this will be our main object of what we're dealing with for the rest of the course. So
this means this z capital, this generating series for so-called you could call it them generalized double Hurwitz numbers because of they are in fact Hurwitz numbers in the simple case of psi. They are Hurwitz numbers, double Hurwitz numbers, and for general psi they do not have any nice combinatorial meaning, but anyway.
Yeah, but what we're saying is that we have almost proved that it's a KP tau function. What I mean by almost is that if we put Q1 over H bar to 1, Q2, and so on to 0, then we have proved it, right? We have proved it because we have proved this again can be represented as this Y of K, right? It doesn't matter. So if here we have 1, 0, 0, 0, then we have already proved it, that this is a KP tau function. What remains is to see that if you allow general Qs, then this also holds, but this we'll do on the seminar. On the seminar, we will prove it. And afterwards, we will have the statement that this is a KP tau function, like I'm saying here. So this is from where we started, that we take this KP tau function. It's called KP tau function of hypergeometric type. And then the claim, which we will devote the rest of the course to, is to show that under certain conditions on psi and q, this guy satisfies topological recursion. More precisely, if you take this general guy, produce from it the numbers h, lowercase h, and collect them precisely as we did with the simple force numbers and the monocle force numbers, omegas, omega gens, then they will satisfy topological recursion. And we can write explicitly the spectral curve. The spectral curve will be, in fact, the function y will depend on these q's, and the function x will depend on psi and y. Is it clear?
So yeah, but till this point, we didn't prove in any case topological recursion, but now we are going to prove topological recursion in the very general situation, and this proof will work for all types of Hurwitz numbers and much wider.
Yeah. So we have only seen in some small examples that the topological recursion works, but we proved it. And we will do this for this general setup, which includes all the types of generalized Hurwitz numbers which I have mentioned so far. Okay, is our plan clear?
Ну, да, какие-нибудь вопросы, ничего не понятно, мы вас запутали с этими производящими рядами разными.
Во-первых, все-таки понятно, в чем разница между U и H?
Ну и вообще, как H появляется? И что это за Z большое?
Разница между U и H непонятна, это просто буква.
Нет, это формальные переменные.
Причем это одна и та же буква.
Ну, не совсем. Не совсем. Это мы можем...
Нет, правильно.
Одни и те же числа, вот эти H числа, связанные числа Hurwitz, да? Простые. Их можно собрать в производящую функцию двумя способами. Можно собрать, умножая на U в степени m, где m число транспозиции, а можно собрать, умножая на h в той степени выложения минус 2 плюс L, где L это количество прообразов у бесконечности, да? А G это n. Это две разные промышленные продающие функции. Одна зависит от U, другая зависит от H, если вы U замените на H, они не совпадут. Потому что U входит в степень m, а m входит в степень выложения 2 плюс H, которая не равна, а отличается на вот этот вот модуль μ, да? Просто две разные подачи функций для одних и тех же чисел. Вот. Но есть утверждение. Утверждение стоит в том, что, тем не менее,
Ну, можно взять производящую функцию, которая считает числа по родам, и разложить ее по родам. Но оставить в ней зависимость от u. И тогда каждое слагаемое при фиксированном роде это будет тот самый производящий ряд с буквой u, где u следит за числом точек ветвления каждого рода.
Утверждение такое, что когда эти производящие функции написаны в таком виде, как сумма по μ, от двойного шура, μ, да, с каким-то коэффициентом, то очень легко перейти от одного производящей функции по u к производящей функции по h. Вот перейти именно так, что надо, если у вас была производящая функция по u, вот здесь было u написано, а здесь ничего не было, да? То как перейти к производящей функции по h? Надо u заменить на h, еще дополнительно добавить вот здесь единицу на h. И тогда это получится вот именно та вторая производящая функция, буквально. Потому что, как это сделать? Мы посмотрим, какой коэффициент стоит при данном числе. Вот при данном числе h, m, μ должно стоять u в степени m в одной производящей функции. А во второй должно стоять h в степени 2g минус 2 плюс l. Да? Смотрим, получилось у нас так или нет. У нас было u в степени m, в исходе, когда мы через u писали. Оно стало h в степени m, но еще и добавилось h в степени минус модуль μ. Правильно? Но m и g, они связаны вот этой формулой 2g m от 2g минус 2 плюс модуль μ плюс l. Да? И поэтому, когда у вас получилось h в степени m, который из u в степени m, и еще вычесть h в степени модуль μ, то осталось ровно 2g минус 2 плюс l, как и хотели. То есть, видно, число h, g, μ, оно умножено на h в степени 2g минус 2 плюс l, как мы и хотели, просто такой же. То есть утверждается, что вот в том виде, когда это записано через придуманную шуру, вот в таком виде, то перейти от одного производящего ряда к другому легко. Просто заменить u на h и добавить еще один на h отсюда.
Вот в общем случае, когда θ, все на какая-то, эта штука, она по h, это что? Такое есть отрицательное. Оно в отрицательных степенях, из-за того, что мы делим на h чувствует.
Вообще говоря, да, но мы рассматриваем только для связанных. Род определяем для связанных.
Что? А в чем вопрос был? Там просто...
Утверждение, что у логарифма z уже...
Да, у логарифма не будет отрицательных степеней. Да.
Но абстрактно вот эта теорема, она в общем, что там разрешаются отрицательные степени.
Да, как бы теорема в том, что их не будет там.
Утверждение, на самом деле, аккуратное утверждение, что если возьмете логарифм вот этой штуки и логарифм той, то они совпадут просто такой заменой.
Да, в смысле, там не будет отрицательных степеней по h. Поэтому это прикол.
Какой теорема? Вот это пока теорема просто что здесь говорит, что это какая-то функция. Все, больше.
Да, ну вот. А объект, то, что там бывает, естественно.
Ну, а бывает тоже. Вот его встречают здесь.
Не, сейчас, все-таки утверждение в том, что если взять логарифм, то отрицательных степеней не будет.
Да.
Потому что вот мы их только что посчитали по формуле Ремна-Гурвица и вставили там h. Ну вот h именно так входит.
А в пси не бывает константно.
Да, пси начиная с корненицы. Констант не хотим. Ну, это, в принципе, особо ничего не противоречит, если... Сейчас, противоречит, есть константа...
Нет, там обратимость надо аккуратно.
Констант не хотим, потому что, если там будет константа, то что получится? У вас здесь получится бесконечно, для больших μ здесь будет бесконечно большой коэффициент. У вас будет просто сумма пси умноженная в константу по всем во все коробочки, но коробочек много будет. И так мы не хотим. Да. Ну, мы хотим, чтобы ее легко было от нее экспонент убрать от такой функции. Так, еще есть вопросы? То есть дальше мы вот будем доказывать логическую рекурсию для таких функций. Но там придется наложить некоторые ограничения на psi и q, но все равно останутся достаточно широкие семейства, которые включают в себя все, что мы рассмотрели дальше. Так, еще any further questions?
Ну, видимо, надо тогда останавливаться, и продолжение уже в следующий раз.
Да, давайте перерыв завтра. Ну, идет перерыв до 3 часов.